Hello and welcome. I hope everybody is safe and fine. So in this particular video, we are going to look forward for what is called a contravariant vector. Well, as I have speaking about vectors and tensors, this particular video we will be concentrating only on contravariant vectors. So before we go for these contravariant vectors, on your screen there are a few points. Just a quick note. We have noted that what is a vector, right? We know what is a vector. We have given definitions and different examples of what is a vector. We also know what is addition of vector. We have seen different methods, including the tip to tail method, which is a very common method for adding vectors. We also know what is scaling of a vector. Multiplying a scalar with a vector, we get the scaling factors of vector. We have seen different examples. The next point, what is vectors are invariant? Definitely, that has been the main motto. We have given various examples to show that vectors are invariant, whereas the components of vectors are not invariant. That means the components of the vector changes under different situations, but the vectors are invariant, it remains constant. Also, we can tell that vectors are things that add and scale together. So just a quick revision on your screen, few points which will make you understand that we have looked forward for this type of details on the vector part, details on what we did. So we will straight away go to the contravariant vectors, and here is a nice diagram which I would like to show you. Well, I would just like to keep a note that those who have not followed my previous video, I would request them to follow the previous video, because this is a continuation from that part. So this is a diagram. You see the old basis, as we have mentioned earlier in the video, it would be E1 and E2, right? And the new bases are E1 tilde and E2 tilde marked in red. So we have got old and new bases. And from the previous, we have also got the forward and backward transformation, the values. Now, why I'm showing this, I will just like to explain you. Now, considering these coordinate system, now, for example, if I draw a vector, okay, and it points in this direction, right? And it will go like this, right? And I call this vector as V. I call this vector as V, right? And what I'm going to do is that from the new basis and old basis, we are going to extract the value of this vector, right? I'm going to extract the value of this vector. So let me show you. So we will write V and V, because this would be both old and new. So I will just write at first the values of the V. So what do we need in order to have E1? So for the old basis, we need, it seems that we need a complete one E1, right? This part. So I will just write it for here. It would be one E1 plus, and I need how much of E2? So I need, say for example, E2 is this part. So I need around 1.5 of E2, 1 and 1.5, yeah. So it would be 1.5 of E2. So I mentioned here as plus 1.5 E2, right? It's 1.5 E2. And for this part, this one vector, how much of E1 we need? We need 1 unit of E1, right? E1, I mean to say E1 tilde, which is basically this part. So I need a complete E1 tilde. And let me see how much of E2. This one and this one. So I need one E1 tilde and two E2 tilde. So I will just put it across. Let me just write this part once. E1 tilde, and then we have got plus, and I will put it as 2 E2 tilde. So I put these units as 1 plus 2, right? So these are the values. Now, once we have got these values, 1, 1.5, 1 and 2, so we can write it definitely in a form of a matrix, right? So what would be the form of a matrix? Let me show it to you. Right, so here is the matrix. Okay, this would be 1, 1.5. And I will put up a EI in order to go for the new basis, this one. And I will also put up as 1, 2, and this would also I will put up as EI tilde, right? So these are the new parts. So in this way we can write. Now let us summarize it. So from the old basis to the new basis, how do we get over? So I will just summarize in few words. So let me write this as old basis. Old basis. So old basis comprises of what are the units? I will write as E1 and E2, right? And we have got the values from the forward transformation. I need to show that to you. So F will be equal to 2, 1, minus half and 1/4. Okay, and the backward transformation gives the value of 1/4, 1/2, and -1 and 2. Right, so these are the values from where we are getting from this previous. You see, these are the values. Now I will like to show you the new basis. So the new basis, let me write new basis. Okay, so for the new basis, I will put this components as E1 tilde, comma, E2 tilde within brackets. And what are the values that we have received? These are the values which we have received. This is from this, right? 1, 1.5, 1 and 2. So let me write it for you. It would be 1, 1.5, right? And for the new one, we have got 1 and 2. 1 and 2. So the basic idea, you see, behind writing all those lines is that for the old basis, this is the way in which we go. So from here, we have got the new, this one. And from this part, this is 1.5 and 1.2, we are going back to this. So I will just show you like this. This is the way from old, this part, and from again going back from new to old, this would be going from this to back to this. Okay, this is the way. Now we need to apply the backward transformation in order to see that can we get back to this value. I will put a question mark. Can we get back to this value? That means by applying backward transformation, can we get back to the new basis, which is the value is 1 and 2. And that is what exactly we are going to do that. So we will just turn on the page, but it will remain the same because we need to go back to this part. We need to go back to this part. So let us go ahead. So we have got the values of B, right? So what I'm going to do is that I'm going to apply the backward transformation B, okay, which has got the value of 1 and 1.5, right? So I will write it as 1 and 1.5, right? And this is E1, right? So now I will apply the backward transformation with the values of the backward. So for backward, what we have got, let me write it for you. We have got 1/4 minus 1, and we have got 1/2, 2, right? And I'm going to get it with the new basis vector, which is the, with the backward transformation, I'm the old one. So I would apply 1, 1.5. So what I'm doing is that I'm just multiplying these two factors, So what will we get? It's quite simple. So we will put it as 1/4 multiplied by 1, this one. We are adding plus 1/2 multiplied by 1.5. Clear? Then we have got how much? -1. So -1 multiplied by 1 plus 2 multiplied by 1.5. So I think it is quite clear. What we are doing is just adding and then adding the two matrices. This is 2 by 2. So what we get from here, we get 1/4, right, -1. And if we solve this part, we get 0.75 plus 3, right? So further solving, what we get, if you do the calculations over here, what you get is this one. I will need to write it in red, 1 and 2. Right, so you see this 1 and 2, which I was talking about, this 1 and 2. this 1 and 2, right? So now you see that we have proved by applying backward transformation. So backward transformation means which value? Backward transformation values are which one? You see in this page I have shown you the backward transformation values. 1/4 minus 1, 1, 2. Multiplied with this backward transformation, I am multiplying the values of 1, 1.5 and 1 and 2. How do we get this one? This 1, 1.5, 1 and 2. I have just done this. Simple, right? So we have done this, we have added this part only. This is the new one. So with the old, with the backward transformation at the old basis, we have got this part. That is why I put up a question mark. So backward transformation multiplied with the old basis vector, we have got the new one. So this is already proved, right? This part is already proved. So by applying backward transformation on the old components, we find the new components. Now, so this is the backward transformation. B signifies backward transformation, just to show you once more. So backward transformation applying on the old vectors. These are the old vectors components. We go where we get the new components, which is 1 and 2, which is written in red, and this is that one, which is the red portion, which is the new components, right? Now we can just summarize. So finally what we can write? We can write in this way. So just follow me, because this would be quite easy for you to understand. So if we write here 1, 2, and I put it as EI tilde, that means that this one would be equal to, this would be equal to the backward transformation. What is the backward transformation values? Earlier we have note 1 and 1.5. 1 and 1.5, right? And so we put it as EI, this one, okay? And also what we can write on the other way is that 1, 1.5, this matrix, this part, which is EI, which is the old one, is equal to the forward transformation if we make it with the new one, 1, 2. And I put it as EI tilde, right? So now you see what the basic thing is, that for basis vectors it brings from old to new, but for basis vectors it is bringing for old to new, but for other it is for basis vectors forward transformation brings from old to new, and for basic and backward transformation brings new to old, but for vector components forward transformation brings from new to old, and backward transformations from old to new. So now I would like to explain you here is that, see, this one is the new one, this one is the old one. So in general, say for example, if we go for, let us say, forward transformation, in general, what does it mean? In general, forward means that it would be basically from new, it goes from new it will go to old. But see, here it is happening the reverse way. It is from old we are getting to new, right? So but it is not true for basis vector. Basis vector is taking from old to new forward transformation, and for backward transformation it is taking from new to old. But for vector components, forward transformation is bringing from new to old, and backward transformation is giving us the new from the old, and forward is giving us the old from the new. So it is quite opposite. So why vector components transform in the opposite direction? So why vector? So here I would like to now show you another picture which I have drawn, and this would be clear up much clearer concepts. So here you see, okay, what it is showing: old basis vectors E1, E2. By forward transformation we have got these values earlier. Now you might get confused that where from I have got these values. I have got the answer ready for you. See, it was just at the beginning. See this one, right? So 2, 1, 4, minus 4, this is there. So this one. So old basis vector forward gives you this. New basis vectors gives E1, E2, 1, 1.5, right? Now you see that old components, it is in the different way. Forward transformation is this one, 2, 1, 1, 4, 1, 2, and backward transformation is this. However, the old components are this one, and it gives you the new. So I can draw it. It would be something like this, you know. It would be something like this in this direction, right? And the new components would be from this to this direction. So I need to put a reverse kind of a arrow So this would be from new to old. From new I am going back to old. So this is the difference. And from here what it happens? It is straightforward. So from old we are getting back to the new. So arrow is this direction, and from new we are getting back to old, this one. So for basis the transformation is quite clear, old to new, new to old. But for components it is that new is giving back old, old is giving back new. Here we have to pause. Now we have to take a breath and we need to understand that why it is happening so. Now this is actually where contravariant vectors come into the play. Alright. So contravariant vectors means that they are happening in opposite direction. So it is not here, it is in this way. So now we will come to the next part of the video where I have to keep those pages intact because I'm going to need this. And what I'm going to show you is that why is this, I won't say strange, but it is a different kind of a behavior which the components do exactly in the opposite direction. So now what I will do, I will again draw xy coordinate and I would like to show you an example. So now let us say, for example, we have got the same thing. We have got E1 and E2, right? So I will just put it as E1 and this y direction would be E2. Clear? Now we have got another vector. Say for example, I will draw it again in green and this is this vector which is V pointing in this direction. Simple. This is V, right, pointing in this direction. And the components of V here is more or less simple, 1 and 1, right? This is round about 1 unit of component vector. Now say for example, if I increase the size of the basic vectors to 2, that means what? That means I am scaling it. So I can write over here, what I am going to do is that I am going to take E1 equals to 2E1 and I am also going to take E2 is going to 2E2 with an arrow on the top, right? So let us see how it looks like. So we are going to scale the vectors and we have got enough examples in the previous video, so it won't be much difficulty. So it would become this big, right? This one. So we put it as E1 tilde and the y axis goes to E2 tilde, right? So this is the way in which it has scaled up, right? So the vector V starting from here goes round about the same. So it stays in the same direction, right? And what has happened is that if you see this part compared to this part, I think this is visible, right? So this one was 1 and 1. So what has happened is this part has almost become a half. So I can write the components of this as half and half, right? So the basis vectors go to a scale of 2, right? The basis vectors are grown to a scale of 2 and the vector components seems to have shrunk by a factor of 2. It has grown by 2, 2E2, 2E1 and this has become half. V has become half. So this proves what? This shows that vector V is invariant, right? Vector V remains invariant though the basis of the vectors have increased. This one and this one has increased the size. I will show you another example. I will show another example which make things much more clear. Say for example, we have got another kind of a component. We have got another axis, and this is something like this. I'll take it rather simple, x and y, right? And we have got a vector which is pointing in this direction, right? We are mentioning this for our convenience just as vector V. This angle is theta 1, right? And this angle is theta 2. So this one is theta 1 and this one is theta 2. More or less, let us assume that it is going in 45 degrees. So I can call from here, I can say from here that theta 1's value is more or less equals to theta 2. I mean to say both the size. Now, say for example, we rotate it. We rotate this vector. That means it is pointing in this direction. We will rotate in this. So how will it look like? So I will draw it in red. So somehow after rotation, it would look like this going in this direction and this the part coming in around this direction. So we have rotated this one, right? So this one, if it is E1, I can talk it as E1 tilde, and this one again becomes E2 tilde, right? So E1 and E2, and for your convenience, let me write it as E1 and E2 for here also, so that it becomes clearer. Now you look into the way the vector looks like. So this particular vector, which is in black, so it would be going round about this direction. It would be invariant. It would be invariant. But look into the angles that they are making. So this one theta 1 and this one theta 2. Here it happens that angle theta 1 is greater than theta 2. It seems that angle theta 1 is greater than theta 2. Why? Because, and it also seems that the vector, though it is invariant, it seems that theta 2, this vector v is leaning towards this theta. Leaning towards theta 2. That means what I can tell from here is that if this has moved in this direction, it has moved in a clockwise direction, this one. If this has moved in this direction clockwise, right? If this has moved in the clockwise direction, the vector component seems to be moved in an anti-clockwise direction. This has moved this way, but this seems to be moved in that way. Are you getting my point? Quite clear. So if this has moved in this direction, this has moved towards this. So this angle theta 1 greater than theta 2, and this angle theta 2 seems to be leaning towards this one. Leaning towards this. This is E2, right? So what you need to understand from here, that there are a few points which is now on your screen, and what you need to understand is this. Basis rotates clockwise, components rotate, I'm so sorry. Basis is rotated the clockwise, components rotate in the counterclockwise direction. Basis gets bigger, components will shrink. Basis rotates the way, in one way the component, and the components rotates on the other. So this brings us to what we call contravariant vector. So contravariant is something which is opposite. Contra, we know contra in general in literary part, we need, that contra means actually opposite, right? So a contravariant vector has components that contravary with a change of basis of components. That means it happens in exactly the opposite direction. Contra means reverse, right? Hence with the basis it behaves exactly in the opposite direction, and we have shown you examples for that. So basis rotates clockwise, it rotates on the counterclockwise. Basis becomes bigger, components become shrink. So whatever the way basis is behaving, the components are behaving on the other way. So this is a classic example of what we call it as a contravariant vector. So a contravariant vector has components that contravary with the change of basis of vector. Contra means reverse, and hence it behaves exactly in the opposite direction. These are the two examples which shows that when the basis has been increased, the vector remains invariant, yet it has shrunk down to its size. When the angle rotates in this way, this is leaning towards this, and it seems that the angle is leaning towards the new component, which is E2. So this direction seems to be in this direction. So I will like to show you this part again, as we have shown it earlier. So this again clears up the components, that the old and the new components. These old components give back to the new components going back to the old components. So now we are coming to the final part of our video, and the basic objective would be that if we can prove this in n dimensions, that is not only in 2 dimensions, these are all examples of 2 dimensions. Now we need to see that if we can prove it in n dimensions. So what we need to do is that now we need to write, so in order to do that, we can write the old basis vectors with old coefficients. So let us quickly write this part. So here we are. So we will put this as V equals to V1 E1, right, plus, I won't take much time, I have to finish it early because already it's 24 minutes, V2 E2 plus dot dot dot, and it goes up to Vn En, right? So we put this one. So what we are doing is that we are taking the old basis vectors with the coefficients of the old components. This is the old basis vector with the coefficient of the old basis components, and this can be written in this way. We take a summation factor, we take a summation factor, and I would like to summarize this as I'm lighting it in blue. So this can be written something like sigma j equals to 1 to n, right, and vj ej, right. So I put an arrow over this. Similarly, what we can do, we can take the new basis vector with the new coefficients onto the new component. So what it would be, so we will write it as v. So we write it as v, and we take it as v1, and here I have to put a tilde. So here I have to put a tilde in order to mention it. So v1, this would be equal to E1 tilde. This is taking a time because otherwise it would become confusing. So I have to swap between the pens. V2 E2 tilde, and it have to go dot 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 up to plus Vn En tilde, right. And this again can be summarized. This again I can summarize as a summation. So let me write it for you. This would be j equals to 1 to n, right, and this would be vj. I have to use this color again. So it would be vj, and this again I have to put a kind of a tilde over that, ej, right. So now you see that what we have done over here is that we have done the old basis with the old coefficients, we got this, and with the new basis we have got the new coefficients. So now we can write it as a summary. We can write v equals to sigma of j equals to 1 to n vj ej, and I have to put an arrow. This would also be equals to sigma of I. If I taking j, then the next coefficient I take it as I, equals to 1 to n, and this one would be vi tilde and ei tilde, right. So this is how we sum up. Now what we are going to do is that let us take the backward transformation. So for now, let us take the backward transformation. So for the backward transformation, what we would do is that I will take the this part. So ej equals to, I'm taking out the backward transformation, right, which if you remember equals to I equals to 1 to n, and this would be backwards, so it would be b, right. B for backward transformation. Indices would be b, j, I, and ei. This would be ei tilde, right. So this is with our old basis. So this is the backward transformation. Now what is our old basis? We are taking v as the old basis, right, and we have to take the values. So we will just put it as j equals to 1 to n, right. J equals to 1 to n vj ej, right. This is the old one. This is basically our old component. Now, right, now you see here ej, this ej and is this ej. That means I can substitute this one over here. This ej will get substituted. So what it would look like? This would look like something like this. V, the old component, would be equal to sigma of j equals to 1 to n, right, vj, right, within braces. If I take the indices, I am substituting, so it would be I equals to 1 to n, right, I equals to 1 to n, b j I, and this time it would be ei tilde, then I will close the bracket. And if we do further calculations, which I have made in a short way, this would be equal to sigma of I equals to 1 to n, and then I put a big bracket and I take this value sigma j equals to 1 to n b j I v j bracket closed e I tilde, right? So now you see this bji. So we have just done a summation. So this bji is basically the vi1, which is this one, right? So this becomes quite clear. So what we have done is that we have proved here that backward transformation, that from old to normal, move from old to new, we need to use the backward transformation. So definitely now I can write it in blue just to get a kind of a summary. So this one I can write it as vi tilde equals to sigma of j equals to 1 to n, then we have used backwards, so bji vj, right? So you are wondering, this b denotes the backward transformation, and you have seen here, let me see, no, it is in the earlier page, so let me find it out for you. Yes, this one. No, it is in this page. I'm so sorry. So you see this one, which is the vi, which was the this indices. This matched with the this one. So this proves that we have proven that to move from old to new, isn't it? This from old to new. This one is the old. I am moving to the new part, right? We have used the backward transformation. So from old going back to the new, we got the new one, vi. So we have got the backward transformation. Now let us see that can we find out the forward transformation. So it would be similar. So I will just quickly put the equations for you. So we have got for the forward transformation, we will use the new basis. So let me write it for you. It would be ej tilde, and it would be equal to, so I have to bring out the forward transformation, right? So sigma of f, that is for forward transformation, ji ei arrow. Right, this is the forward. Similarly, you have seen the backward, like in the previous we have started with the backward transformation, right? This one, yes, this one. So this is the forward one. This is the backward one, right? So for going for the forward transformation, we get this part. So now what we need to do is that we need to find out the values of v with the old one. We start with the old. We are always starting with the old basis vector. So ej e f j I e I is equal to, and the backward transformation was this one, I equals to 1 to n. So this would be the same thing. This is bji, I equals to 1 to n. So fji, it would be I equals to 1 to n. That was a small error from my side. So let me write it quickly for you. So we bring out v equals to, this time same, sigma of j equals to 1 to n vj, I put a tilde over that, and then we have got ej, right, tilde, right? So now you see that this ej, again I am substituting the value. I am doing all this calculation so that it becomes easier for you. So once we put this, this becomes v equals to, I am just doing a shortcut. So this becomes equals to j equals to 1 to n, okay, vj tilde, and then I arrange the brackets. This one is sigma I equals to 1 to n f, this is a forward transformation, so f j I e I, right? And then what we get from here, we get this, we get sigma I equals to 1 to n, then within bracket sigma I equals to 1 to n, sigma j equals to 1 to n, right, this part, j equals to 1 to n, f j I vj, right, again a tilde, bracket close, ei, right. So this is this part again is the vi. This is the old one. This is the old one. So now again you see what we can write from here is that vi equals to sigma of j equals to 1 to n f forward, because we have got the forward one, ji vj tilde, right? So we are almost at the end of this. We are almost done. So this proves, what does it prove? So this proves that to move from the new to old, we use this one, f, from the forward transformation. And to get this one, to get the backward transformation, to move to the new basis vector, vi, we have got the backward. So exactly it is the opposite. You see this one and this one. This is the forward, right? This is the forward transformation. So this we have used, this one is the vi, which is the old. So we are getting to the old using the forward, right? But it should be reversed. In order to go, in general, we mean by going back to old means we are moving back. Going to new means moving forward. But here it has happened exactly opposite. So now I would like to show you the final summary. I have already made it in a piece of paper. So you see ei. Now just few important points before we wrap up. So this is the basis vector transformation, right? Okay, this is visible, yeah. Okay, so this is, okay, let me put up a fresh new page so that you can understand. This part. Okay, so now you see the basis vector ej, it is the same. In order to get to the new basis vector, we are doing the forward, and in order to get to the old, we are doing the backward. Quite clear. That is for basis vector. But you see the difference over here. In order to get to the backward, we are using the new one, and for the forward, we are using the old one. So for vector components, this is what I can now write as contravariant. Contravariant means it is happening exactly in the opposite direction. So it is a contravariant part, right? And this is the same part. So this actually is a summary. So I would again like to tell you that for the basis vectors, this is not a problem. In order to get to the new, we make the forward. In order to get to the back, we take the backward. But for vector components, it happens in contrary. In order to get to the new, this one, in order to get, we have to get doing the forward one. For the old, forward, and for the new, backward. So now I will just show you how the indices actually behave. This is something I would like to show you in black pen, because there is a little bit of summation which we need to understand, because Einstein's field equations will have this one. So you see, if I can write V equals to a sigma, okay, of I equals to 1 to n, right? And we are doing the same one, Vi, okay, Ei, and I put an arrow, is obviously equal to what we have achieved, I equals to 1 to n, Vi tilde, right, and Ei tilde, right? So now you see that these two indices are contravariant. Which one? This part I am marking in red, and this part. These two are contra. These two are contravariant. Why? Because this is the old one, this is the new one, right? So we make the change and we can write it in this way, right? So in order to identify that these are contravariant, we put the indices on the top. So we write V equals to sigma of I equals to 1 to n, right? This remains the same. And then this V this I, this one moves on the top. This I moves on the top and this remains at the bottom, EI. This is the basis indices. And again I will write it as sigma I equals to 1 to n, right? And this V, this one again will go on the top. So V, then it will become I, and this will have a tilde. And the red part, that is a new one, EI will be remaining the same. EI will be remaining the same. This is an arrow. Yeah. So this is what is these are the basis vectors. This one, this would be I. This one and this one is the basis vectors which remains at the below, and these two, this part and this part, these are the contravariant vectors. So it reminds that the contravariant vector moves right on the top and the basis vectors remains right at the bottom. But do not get confused with exponents. Don't worry, because in tensors and in general of this kind of a calculation, exponents generally do not come up. They don't really pop up. So that brings to the end of our video. So I'm so happy to share exactly the, how things have happened. I won't take again a time to summarize those things, because this is basically the summary from old to new, the old components and to new components. This is a wonderful example which shows that the vectors remains invariant, but the vector components, when they change, how the vector components behaves in a contra way. This angle theta and theta also shows that it moves clockwise, it moves in the counterclockwise direction. This has been a fairly good calculation. And finally, this one. Just remember this one, old basis to new basis, old components to new components. And this is also equally important, which shows that for basis vectors, it is quite a straightforward process. But for vector components, it happens exactly in the opposite direction. So this is how it brings to the end of our video. I think you have liked it, you have enjoyed, and the next video would be on the basis of covectors or this is contravariant, that would be covariant vectors. So my next video would be dealing with covariant vectors. I've also shown you that the this part, which is the contra and the vector components, let me find out. Okay, I have also shown you that how the indices behave and how the indices move from upper to lower. So that is basically bringing to the end of the video. This is the summary of everything, and it actually shows you how things behave under co and contra. I think it has been a little bit long video, but just put up your comments. Just put up your comments if you're anything missing in this video, if you want to make further videos and how things are. And yeah, that's all. So I think you have liked it. Watch out for the next video, which would be opposite. The contra is done. Now we will be proceeding with the covariant vectors, and then finally with the linear mapping, and finally to the metric tensor, which is our basic objective. So just keep it in mind how the indices do change, when you are moving. So you can move the indices from top to bottom, and then you have to make it from bottom to top. So that is how the co and the contravariant vectors behave. So just stay happy, stay safe, and wish you a happy weekend ahead. Thank you very much.